Hi. Hi everyone. Hopefully you can hear me. Thanks for coming. uh, Last week, we covered DNS in deep detail. That's still up on Twitch. That'll go on YouTube along with a bunch of other previous videos that I've yet to upload. But that was by far the most popular of these streams so far. It had hundreds and hundreds and hundreds of views. I think even maybe over 1,000 just on Twitch. So I'll try to do more network protocol deep dives and other similar things. And if people have other network protocols they'd like to dive into, or other aspects of DNS they'd like to dive into, let me know. But we're going to go from those heady heights of incredibly popular topic, which clearly had a lot of broad interest, to a topic that's maybe a little more niche. I've put this out in the poll a few times and it never got the top number of votes, but had a few people poke me and go, but we really want this one anyway. So I'm like, okay, well, I'm just exercising total control over the process, and I'm bumping it up. And I'm going to talk about functional programming in C. Sorta. I'm going to talk about some of the functional programming techniques I've learned from and used the most in C programming. But really, they're just techniques that can be applied to any programming language. And I found them really, really useful ways to think about code and to think about programming, and found it really useful stuff for making my code simpler and easier to follow and easier to think about, which I think is probably the most important thing about code, right? Like, another word for code is instructions, right? Like, ultimately, all code is a set of instructions that, the computer has to go follow in order to carry out a task. But we all call it code, right? Because it's so hard to read, right? Like, it's literally code to most people, right? And I'm a strong believer that, the first and primary job we have as programmers or coders is kind of decode it. It's to make it as unbelievably simple and easy to follow as possible, and to have the lightest cognitive load whenever somebody's reading your code, which might be you a little later, right after you wrote it and you forgot some of the details, or somebody doing a code review or whatever, right? Or somebody extending it or modifying it. But that making code as simple and as easy to follow as possible is just the most valuable thing we can ever do. You get sustainability and maintainability benefits, but you also get security benefits, right? And a lot of that boils down into asking as little of the code reader as possible, right? Providing them with as much context in one place, providing them with like a clear flow to what the code does, and providing them with, only doing one thing at a time. Try not to confuse the reader. Just like any kind of good writing, right? If you're writing a novel, like that, all those things might be applicable too. And when I was learning to code, my first programming language was BASIC. Probably like many people here. If you look at the background on the Twitch screen, it's a Commodore 64 screen, and that was the first place I ever learned to code. And after a pretty short stint with Pascal, I started learning other, mostly, what are called iterative or very traditional like programming languages, things like C and C++ and JavaScript, although at the time it was called LiveScript, and eventually Java and so on. And for me and my background, functional programming languages seem very scary and exotic and hard, and it seemed like only like the very elite people were into them, or people with insane coding capabilities would somehow gravitate towards functional programming languages. Let me just ground things. I'm going to switch to a document view for a bit, but like, it's very standard way to divide up programming languages, right? Is you've got I'm going to call them boring. There's a few different names for this type, but I'm just going to call them boring programming languages for the moment, right? So, but like basically the C family, right? So you've got languages like Pascal and C and C++, which is an abomination, but we'll leave that out here. JavaScript, Java, like let's say even Python. Like we could list all sorts of languages here, right? I would put like Perl in this category, probably Ruby, all sorts of things, right? And this family of programming languages, there's a lot of folks familiar with like one or more of these programming languages, and they kind of have some mutual intelligibility, right? Like if you know one of these well, you're probably going to learn another one of these like pretty quickly, right? You're gonna have some pretty familiar concepts and structure to pull from, right? And there's implementation details. Most of these are compiled languages, right? A compiler takes the code and turns it into machine code that can then be executed, and that just happens once. Some of them are interpreted and have or have runtimes, right? Like Java can interpret bytecode at runtime and do certain kinds of optimizations because it's happening at runtime that a statically compiled language can't, and so on. But like at the surface level, as code in an editor, they more or less kind of look and feel the same. You've got your typical functions that are declared, and they just do things, and they call other functions, and you might use OO techniques or whatever, right? But you all know what I mean. And then at the same time, right, we've got functional programming languages, which are considered very different, their own family, right? So we've got like my first one that I learned was Common Lisp, right? So that's pretty cool. Then there's other dialects of that, like things like Scheme, which a lot of people have learned because it's pretty common choice in some programming books and tutorials and so on. All the way up to there's modern incarnations or modern takes on some of this. Scala is an interesting language that kind of blurs the line, right? And there's kind of a schism in like the programming world about how to even think about coding, right? Like there's these, what I'm going to say, the boring or traditional languages, which kind of inherit their architectures and design from, say, like von Neumann machines, and how instructions are processed one at a time in a machine in a certain order and so on. And so these are kind of an abstraction on top of that, versus functional programming languages, which are kind of an abstraction on top of like lambda calculus, or things like Church was coming up with. Don't worry if you don't follow all that. That's just some history lessons. But they're very cool, and there's a lot we can learn from these functional programming languages, and a lot I learned. Like I spent a long time really not understanding any of these programming languages, and I still don't really code in them very much. Like I've never built a production system that uses a functional programming language. Just never. And I think it's exceedingly rare. There've been a handful out there where folks have built some, and I think they generally fall into disrepair quite quickly, like after anybody who was involved in building it leaves, because it's very hard to sustainably hire people to maintain that stuff, and so on. Scala is pretty popular, and we here at Amazon have production services written in Scala. I didn't write any of them, but we do have some, and Scala does blur the lines, and that's probably a little bit of an exception to that. But they have some common concepts, right, that are kind of central to functional programming, like functional programming. And I'm going to just off the bat say that a lot of them are like useless, right? Like there's a lot of like hipsterism and just like, well, let's be different for the sake of being different, and a lot of like esoteric, mathematical, self-referential like madness that can happen in the functional programming world. Functional programming tends to be self-referential in a way, regular programming isn't. We'll see in a bit like why, but they've all sorts of concepts that I think can be very intimidating. A lot of people are intimidated by like what a closure is, or how impressed some people seem by closures, or how they seem like super integral to things, or a combinator, or a functor, or a monad. I wrote up a list actually and put them on Twitter. And in my opinion, pretty much all of those things, even including closures, are just like, you do not need to understand those things. Like unless you are super deep into functional programming, or super deep into like language research or compiler design or things like that, they're just not particularly common or useful things. And when people use them to like shame others, or like think, oh, everybody should understand these, or real coders understand those things, it's just total complete nonsense. And I just absolutely despise that like aspect to like the functional programming world. Like I've met a lot of Haskell bros who like take a lot of pride in writing some really terrible code, in my opinion. In the same way that I've met 10 years before that a lot of Perl bros who like used all these like map reduce statements that are just impossible to fit in your head, but they take pride in somehow being able to wrangle complexity. And in my opinion, like that aspect of functional programming, or any kind of programming that's complicated for its own sake, and people start to take pride in being able to wrangle that complexity, I think it's almost a toxic instinct. C++ is another example of that on the other side of the fence, so it can happen anywhere. Someone's commenting that closures are pretty common and so on. I'm not saying closures aren't useful. I'm just saying you don't need to know. Just saying they don't need to, like, they're not mandatory knowledge, and no one should feel ashamed if they don't understand what a closure is, or if they've never programmed using a closure. If you do learn what closures are, they're awesome and can be very useful, but only use them if you're sure like everyone you're coding with has enough context to be able to follow along, right? Like, and closures are definitely a lot simpler than combinators and monads and so on. So they're not so crazy. Now, when I was in my 20s, I decided, okay, I'm gonna learn. I'm scared of this functional programming stuff. I'm gonna learn it, right? I'm gonna really try to figure it out. And I did. I went and read some books, and got through all the exercises, and I got to the point I could be pretty literate and actually code in them, and build reasonable sized projects. And right now I could probably knock out a working program still in a bunch of functional languages, just for the fun of it. And what I took away, I found it was kind of like learning a different speaking language, right? I grew up being bilingual. I grew up speaking Irish. I'm from Ireland, and my parents speak Irish at home, and then I went to an Irish-speaking school, and most of my friends would speak Irish. But then with the broader community in Dublin, the part of Ireland I lived in, it's English-speaking, so I'd speak a lot of English too. And I think very differently in Irish than I do in English, right? Irish is a language with far fewer words than English, and so there's more double meanings, there's more poetry to it, and you just kind of go about things a little differently. And then when I learned some other languages later, like I learned German and Dutch, although those are quite similar to English, I'd find, I'd think even a little differently then too if I was using those languages. And I found something very similar happened when I forced myself to learn how to use functional programming languages. And the biggest takeaway for me, like the biggest thing I learned in a deeper sense from functional programming that I hadn't learned as deeply from regular programming, right, is that functions are data, right? because there can be this sense that, okay, you write your code or a function in an editor and you give it to the compiler and you get what you get. You get some machine code, the compiler tried its best to optimize it, and that's that, right? And then the code lives like that eternally and executes on whatever inputs it gets when it's running, right? But in functional programming, there's a much stronger sense that, no, the function itself, the code in that function, it's just data. You can change it, right? And so some obvious implications of that are, you can do like runtime optimizations, right? You can go, hey, this piece of code that we've got in our program, we're never really using that, so let's get rid of it. Or we want to use it a different way, so let's rewrite it, like while the program is running, right? Which is this kind of a mad concept. Or even just the simpler sense of this, that like, well, if a function is data, if it's just data, then I can do things like have the function be the result of a lookup, right? I can have that function be in like at the end of a hash table, right? And this is probably the biggest thing I learned and one of the biggest takeaways that I've applied to C programming. And I'm going to show you how we use it in S2N, which is the SSL library we use here at Amazon. It's open source, it's on GitHub, so I'll just go through it there. And we use this concept to deliver some pretty major simplifications. And so let me switch screens a bit. Might have to change which screen it thinks I'm using, but we'll see how that goes. Da-da. Yep. Oh, wait. Hopefully you can all still see me. Oh man, how do I make Twitch pick a different window? Let's go figure that out. Alright, here we go. Select a game. Twitch is designed for gaming, so it keeps thinking we want games. Alright, let's go. Found it. Where's Safari? Alright, here we go. Alright, hopefully you can see my Safari window on screen, and we're going to make it much bigger. Don't worry. Let's go over here. Okay, so that's probably about as big as I can make it. Let me see. Ugh. Okay, that should be more clear. So, great. All right, we've got our first view. Now that I can flip back and forth. So, at the core of doing SSL and TLS, right? There's a state machine, and so like if you're doing an SSL negotiation, right? You've got a client, and you've got a server, and there's a bunch of states that you have to walk through, right? So the client, in TLS, the client says hello. That's the very first thing that happens, and it sends that to the server, right? And then the server responds with its response, right? Which can be different depending on whether it's resuming a connection or whether it's trying to establish a new one. But the handshake kind of goes back and forth a few times, and you get these different states. But let's say this responds with a server hello. The state machine doesn't always follow like exactly the same chart every single time. It depends, like I said, on whether there's resumption, whether there's something called forward secrecy happening as part of the handshake and so on, but it doesn't really matter, right? What does matter is that the client and server each need to know where they are in this state machine and need to be in the correct state, right? And need to be going back and forth. And so they need to agree about that, right? And now this is a really common problem, right? This is a really common coding thing, building state machines. And traditionally, the way people have gone about this is by using branches in the code, right? So they've got some piece of code that's running on the server side that's like, well, if this message comes in, like if I see a client hello message, then and this happens inside the if statement, right? Well, then now switch to the server hello state and send the hello server hello, and then remember what state I'm in. And then, the client does some stuff, sends back its response, and then the server goes, okay, well, if I was in the server hello state, and then I get this message from the client, and so on. And state machines can start to get pretty complicated pretty quickly, because you got to track, what state you were previously in, whether you're meeting all the preconditions for transitioning to the next state. And if you're doing it in a protocol like this, you might also be interleaving all of this with message parsing, figuring out what's in messages and so on, and it can get pretty messy. If you want to see an example of that, the way OpenSSL does it is they've got this file called s3_server.c and s3_client.c, which are both many thousand line files that are the client-side state machine and the server-side state machine for SSL and TLS, and it's a gigantic piece of code that uses branches and switch statements to keep track of what's going on where, what state it's in, and what messages we should be parsing and so on. And I honestly recommend sitting down, reading that file, and never ever writing code like that in your life. Just aspiring to never write code like that. It is impossible to follow, very, very difficult. I don't mean that as a disparagement of the OpenSSL project. It's just something that kind of grew up organically like that, but it's just really, really hard to follow. And so, and there have been security issues. There was a security issue that's actually cropped up 3 or 4 different times in different SSL libraries, including OpenSSL, where you could trick the state machine. The client could send a message earlier than it should have, and the server would just go, okay, I guess I'm in that state now, and skip a bunch of important security checks. So, for example, the client could send a change cipher suite message before any secure keying had happened and force the server to use an insecure key. Not a great security issue. So we decided to do things very differently in S2N. And in S2N, we built our state machine in a file. So this is on GitHub. This is the S2N handshake io.c file. And it is pretty much directly inspired by functional programming techniques. And so the core state machine itself is really, really, really small. It's a tiny C function that basically just advances things to the next state and will only advance things to the next state, right? And that's way down the bottom here somewhere. Let me find it. There we go. Advanced message. There's not much code to this, but it's basically just you saw the whole thing there, maybe 20 lines. That's actually what's transitioning between the states. And if you look at the top of this file, right, from this semicolon all the way to the top, as I scroll here, all these huge declarative sections, so these are just this is just simple declarations, are declarations of valid state transitions. So I'll explain what all this means in a bit. Don't worry. And then that go into these state machine tables, right? And so let me start to decode some of what's going on here. So the key trick, what we're doing, right? This state machine array, right? It's an array of structures And it's got every so in C99 you can actually label the indexes in an array. So this notation here where it says client hello equals, that just means like, well, the 0 entry equals and the server hello the 1 entry equals, right? So these are just numbered entries, but we've labeled them like this so it's a lot simpler to read and to follow, because again, making things easy to read and follow is like the #1 thing we can do when we're writing code. And basically for every message type that's in the state machine, every state that's in the state machine, we have an entry, right? And that entry records a few things. It says what the record type is, so that's just a detail of the TLS protocol. It has different record types for different parts of the state machine. The message type, right? So that's the message we expect at that time. Whether it's a client or server generated message. So C here means the client sends it. S means the server sends it. And right down there at the bottom you'll see a B, which means both sides can send or receive that message type. And then we've got 2 function pointers, right? We've got a function pointer that the server side should call and a function pointer that the client side should call, right? So here we're using functions as data, right? The functions themselves that we're going to jump to and call are just entries in this state machine table, right? And so instead of coding it like in an imperative style where we've got like a gigantic switch statement or a lot of branches about what state should be called when, we've instead declared it declaratively, right? Like we're just writing down in these simple declarations, you know, for each state in the state machine, here's some properties, right? Like it should be sent by the client. Here's the functions that either generate or receive that message type, right? Here's the record type for that, and here's the TLS message type, right? So those are the entries for each state in the state machine, right? And then separately, we have this definition of we've got the same for TLS 1.3. It's a little different, so it's got its own entries. We call different functions in some cases for TLS 1.3. But then we give all these messages names. That's just for like debugging. But then when we get to this table on line 146, what we do is we fully define and fully linearize. Like here is the legitimate state order of states, right? These are the only allowed orders of state, right? And we've got this fake one called initial that we initiate the process, any connection in. They start out in this initial state machine because we don't know what path we're going to take yet at the very beginning. And so every time we start a new SSL connection, we start off in this initial state machine, which just allows client hello and server hello, because we know we're always going to do those, right? Now, by the time we send the server hello, or by the time we receive the server hello, now we know what to expect. We know now at that point the full chart of the state machine. The way the TLS protocol works is once you've sent the server hello, it's basically written in stone now how the rest of the state machine goes, right? And so we've written them all down in stone, right? Like, so here, it just a regular, boring, negotiated TLS session. Nothing particularly special about it. You know, this is the order of states that are expected, right? A client hello, a server hello, a server change, server finished, all the way to sending application data, right? If we resumed with a session ticket, right? If we generate a session ticket, this is the states we would expect in this order. If we're doing a full handshake rather than a resumption, here's the orders we would expect. If we do a full handshake with a session ticket, and so on, right? You can see them. If we add forward secrecy, things change a little, right? And so, again, we're writing all this down in stone. We're doing it in a declarative way, right? And then our state machine becomes as simple as, okay, well, I'm going to know what the valid set of transitions is. I'm going to know which chart I'm on very, very early. So all I have to do is advance, right? I get a message in, I parse it. If it fails, it fails. I throw an error, abort the connection. But if it succeeds, I don't need the function to tell me what to do next. I already know what to do next. I advance the next state in the state machine and call its function pointer, and that's it. And this radically simplifies things, right? And so this act of using the functions as data, right, where because the functions are the pointers in the state machine, we free ourselves from ever having to write if conditions or switch statements or anything like that, right? We just don't have to think about it because the code can figure that out at runtime. It can use these function pointers to just jump to the right place, right? So that's the biggest thing I ever learned from functional programming. The functions are data, right? And so you can use functions in lookups. Actually, JavaScript's a great language where you can do this all the time, right? Functions are data in JavaScript too. It's kind of a semi-functional language. But there's something else going on here too, which I learned a lot from functional programming, which is in functional programming, I would say it's very idiomatic and like highly encouraged to separate any like input or message parsing from business or flow control, right? To make those things completely separate, right? Because when you have a single, state machine or block of code that's doing like, okay, I'm going to manage switching between state machines or states in a state machine, and I'm also going to be doing message parsing, it's really, really difficult. Like it's a lot to keep in your head, right? So this style of programming really encourages you to write just single purpose functions that parse messages, right? So here I've got a block of code that like this it's probably too small, let me make it bigger for you. Like this server hello send function, right? This is all the code it takes to send a server hello in S2N. And it's almost reads declaratively itself because you're really just saying, well, here's what I do, here's what's in the message in order. We'll see in a bit how these functions work internally to achieve some of that. But it's not, there's no like flow control happening in here. I don't have to think about the state machine as I read this code. Also, I have the receive function in here too, in the same file. So if I'm sitting down as a code reviewer and I want to go, well, how does S2N handle this server hello message? It's all there in one place. I can have all that context in my head, right? And it's not polluted by the state machine context. I could just forget about that. I don't need to think about it, right? We have rules in S2N for lightening cognitive load. We try to write short functions. We try to not to ever have too deep a call pattern and so on, and this really helps with that. All right, if I resize the window smaller, all right, let's try. Did that help? I can't tell. Keep complaining if you can't read it. I'm sorry. It's definitely not. I'm trying to make the text as big as I can, but also trying to fit a reasonable amount of text on screen. Great, it seems to have helped. And so that's another like thing I learned from functional programming, right? Super idiomatic thing. Separate message parsing from flow control because they're just it's too much to keep in your head. All right. So then the third thing I learned from functional programming that I think is really useful, especially for C, to help achieve memory safety, is a kind of I/O pattern that I don't see enough of, right? So when we wrote S2N, kind of had to write it in C because we were replacing other C implementations, and so everything we were kind of linking it into was also written in C. And we also had target environments that were extremely small, and we didn't even have like a C++ compiler for those environments. Very, very small embedded systems. And so C99 was the way to go. But I also want to say, although S2N is written and compiles using a C99 compiler, it's very much written in a dialect of C, which is another kind of thing I got from functional programming, right? So when I learned Common Lisp, one of the first things I learned is no one writes Common Lisp. It's not really a thing, right? For the most part, what people do is they define other dialects using Common Lisp, and then they write in those dialects, right? And on the one hand, that's bad because, if you just write in this dialect that nobody's ever heard before, that's not going to be a light cognitive load. That's kind of crazy, right? But on the other hand, if you can establish a dialect and get people kind of bought into it and get people familiar with it, having just a reduced surface area or a reduced kind of footprint to the language that you're actually writing in can be really, really valuable because it actually makes the code reviews go better and the common understanding go better. And so we did this for S2N for that reason, but also because C is not a safe language, right? Someone's asking what our small target environments is. At the time we wrote S2N, our smallest target environment was these things called dash buttons, where we had these cool buttons people could get and stick them to their washing machine or whatever, and you'd press it and detergent would come like a week later or 2 days later. And they're just like tiny little embedded systems, but they actually run SSL as well. And just these tiny little ARM environments, right? And but I'll get back to my main point. So that C is not a safe language in general. It's got all sorts of sharp edges, right? There's all sorts of places where you don't have full memory safety in C, and there's all sorts of places where if things go wrong, you can get in trouble really quickly. And I'd say pretty much all of C's I/O and string handling functions are just terrible. They're just off the table. It's really hard to code securely and use them, right? And so didn't want to even try, right? Instead, wanted to replace them with mechanisms that would be really simple, easy to follow, functional inspired, as we'll see, and deliver safety. And so we have this stuffer. You can see an example of one there of it being used right there on the screen, but we'll see what stuffer is. And stuffer was heavily inspired by the kind of I/O you see in functional programming languages. And I find it just a way easier way to think about I/O and get memory safety at the same time. So I'm going to go back to a document view, right? So the standard way in C to do I/O, right, is to just read and write bytes, right? And then when you've got the bytes in memory, if you want to do something with them, map them to a structure or parse them or serialize or deserialize them, you just kind of do it using raw memory, right? You just kind of okay, go for it. You read in these 4 bytes, you treat it like an int, let's just map it to an int and so on, right? And that can lead to a few security issues, right? So Heartbleed was an example of a security issue where OpenSSL was parsing heartbeat messages and wasn't enforcing the correct size limit on the amount of data it could read, right? So it would end up reading too much data and send it back to the caller, which is really, really bad. Other bugs are buffer overflows, where someone can send too much data and the system isn't really tracking how the size of buffers or how much memory's been allocated, and can end up writing data to places they shouldn't be able to, and ultimately exploiting it in all sorts of clever ways. And we just don't want to have any of those memory safety issues in S2N ever. So so instead of reading and writing directly like that and then just manipulating memory, we have this stuffer concept. And a stuffer is really, really simple, right? It's a structure that has a few things in it. I can show you the actual definition in a minute, but I'm going to do this one from memory. Pretend that's a curly brace and I can draw curly braces. But essentially there's a buffer, right, We actually have a separate data structure in S2N called a blob, which is just basically a buffer and its size. But I'm just going to put them both here, right? So you've got a buffer and a size, right? So those are the most important parts of the structure. So straight away, anytime we have a buffer, we're tracking its size, something that C doesn't impose. And then we've got two cursors. We've got a write cursor and a read cursor, right? And they track basically, how much data we've written into the buffer, and like what the kind of, high point of that is, and how much data we've read from the cursor, right? And there's other things in our stuffer, as we'll see in a bit, and I'll talk you through what those other things do, but this is it. This is the core. Just these things are enough to implement a stuffer, right? And so you've got like a buffer with a size. So this is the size here. And let's say I write some bytes into the stuffer. So let's say I write 4 bytes in, right? Well, if I write 4 bytes in, now that's my write cursor, right? And every time you write, you've got a simple rule to follow, which is never let the write cursor go past size, ever, right? Because then you get a buffer overflow. But it's really simple. Anytime you're writing into the cursor, writing into the buffer, like first check that there's enough space. If there is, add the data, probably after where you've already added some, and then move the write cursor, and just never let the write cursor be bigger than size. And that simple check on its own prevents buffer overflows. This is what's happening in memory safe languages. So if you look at a language like Java, which a lot of Java is written in C, right? But Java has memory safety. How is that possible if it's written in a memory unsafe language? Well, it's doing this. That's it, right? It's like checking, is there enough space, right? And then read cursors, at the start, the read cursor is always going to be 0. But let's say I go and, I want to read 6 bytes. Well, I don't have 6 bytes. I only have 4 bytes because that's where the write cursor is, right? But if I, let's say I want to read 2 bytes. Okay, well, read 2 bytes and then put the read cursor there, right? And if I want to read another 2 bytes and so on, like I can. And that's it, right? And what's kind of inspired from functional programming here is that we force all I/O to go into or out of stuffers like this by just having these simple like nested functions, right? So I'm going to switch to back here. So if we look, so here's the actual stuffer structure as it has evolved, right? We've added a few things over time. I'll make that even a little bigger, sorry. So as I said, we actually use a blob. Anytime we're tracking a buffer, we actually use a blob, which has the size in there. So that's got the data and the size. But in our stuffer, we have a read cursor, a write cursor, just like I said. We also track a high watermark, which is just, we also can remove data from stuffers. And but at the end, when we're done with it, and that's easy, right? You just kind of roll the write cursor back a bit and the read cursor back a bit. But if at the end of a stuffer's lifetime, we want to securely like erase the entire stuffer and 0 the whole thing, so we keep track of what the high watermark was. We also track whether the stuffer was allocated or not. Basically, this gives us a memory life cycle. Like if we allocated the stuffer with alloc or malloc, we need to know to free it again at the end. And so that's what that single bit tracks. We also track whether it's growable or not. So if we did use malloc to allocate it, it generally is growable, right? We can just grow it anytime we want by reallocating it, which is nice and simple. And then we have this tainted bit here, which just tells us is it actually safe to resize a stuffer or not. And sometimes it's not safe because we have like concurrency controls or things like that. But the high water mark again. That's just the maximum position the right cursor ever reached. Just pretty much as simple as that. And then and that's all that's in a stuffer. We've got some simple macros here, which just convenience macros to see how much data is available, right? That's the right cursor position minus the read cursor's position. How much space is remaining, just the size minus the right cursor's position. Has it been wiped? Has it been freed? Stuff like that are just nice utilities. But then we've got all these functions that are oriented around accessing a stuffer, right? So rather than ever asking the stuffer users to do things like serializing or deserializing, we put that into the stuffer itself, right? So you can read an int from a stuffer. You can write an int to a stuffer. And the stuffer kind of routines will just figure it out. They'll do the serializing and deserializing for you, right? Because that's the kind of thing that, if you look at other code bases, they're scattered all over the code. There's many examples where, the coders are doing that over and over again. You can read and write base 64 into a stuffer. We need to do that for parsing what are called PEM files, right? And other things. But, every single one of these functions that reads or writes to a stuffer boils down ultimately to a really, really, really simple function that's just going, well, can I put these bytes onto a stuffer or not? Or can I read these bytes from a stuffer or not, right? And you can kind of see quite quickly how if you're disciplined about it and you just use the stuffer every time you need to do I/O, you're just not going to run into memory safety issues here. It's always going to enforce you. And like I said, this is what languages like Java or Python are doing, right? This is all they're doing under the hood. And the other benefit you get from it, just to go back to kind of another benefit of how all this works, right? If you've got a message format, right? And let's say the message format is a 4-byte int followed by, so let's say that's a 4-byte int, so uint32, followed by a 16-bit int, right? 16, followed by some number of bytes, right? Which is a really common kind of paradigm in binary protocols like S2N, right? If I write the message parsing function, it's going to look like this. It's going to look like read uint32, read uint16, read bytes. And so in 3 lines, I've made really clear what the message format is, right? The message parser itself ends up being declarative because of this simple pattern of how we've oriented I/O. It's really, really powerful. And this is really common in functional programming, this style of things. And you get these really, really nice emergent properties and a kind of recursive beauty to it that I really like, where it forces or kind of manifests these nice declarative programming techniques, even without intending to, that just make everything just so much easier to follow. And that's what's going on. This is probably one of the biggest things we did in S2N, right? Is just use this approach to make things nice and testable, or nice and code reviewable and easy to follow, and avoid as many mistakes. And then the state machine trick I showed you earlier, where we just use a table with all the states and then go between them, is great. And someone's asking, are we basically applying type safety to I/O? Yeah, essentially. I mean, this is a form of type safety, right? We're declaring the types not as an attribute of the variable directly, because C doesn't quite let us, but essentially in the way we're coding, we're getting that effect. And so those are probably the best things I took from functional programming, at least, and applied to C, and feel like it's paying off and getting some pretty decent benefits from. There's more other examples in there, another common programming technique in functional programming languages is to use macros, right? To just keep things every tight. Now macros mean something a little differently in functional programming than they do in C. Macros in functional programming languages tend to be a runtime thing where you're changing the behavior of functions at runtime. In C, macros are pretty much a compile time thing, but they're still a very useful utility, and we've got a lot of macros scattered around S2N, and it gets us this nice performance benefit too, where things can just happen right there at compile time. But yeah, that we're gonna keep things relatively short today. I don't have much more to say about functional programming in C, at least as it relates to S2N. I should, I guess one concept that's worth just, reminding people of is like that style of state machine table that we saw earlier. It's also inspired by jump tables. And if you've never seen a jump table, they're worth looking into and how they work. This style of jumping to a certain point in code based on a value can be useful in different ways. I've done that even in Java, where you can use Java reflection to put functions as values in hash tables. We've got a DNS parsing library here that I wrote that used that technique in. I think it saved a lot of code. And I'm all about saving lines of code and making things as easy to follow as possible. All right, I'm gonna scan all the comments to see what I missed, and then if people have other questions, get them in now, because I'll get to them then at the end, and then we'll probably wrap up. Oh wow, there's a lot of comments today, more than last week, which is interesting considering we had more viewers last week. All right. Scala is a functional language, yeah, and it is fair to describe it as an everything language. Scala is an everything language, as is JavaScript these days too, right? Like, and Rust is trying to straddle some boundaries too. So things are fusing, and I feel like the best parts of functional programming languages are finally making it into the more common everyday programming languages, which is awesome. And the same with F#. I've never coded in F#, gotta admit, but looks cool. Certainly got a cool name. There's the point about closures that I already asked. Someone is saying they saw a 15-line map grep expression in Perl, and that the person was very proud of themselves. I have seen this too. I've seen Perl scripts with these things in them, and I know that Perl has this motto of there's more than one way to do it. And as a utilitarian language, if you're just like writing a script for your own purposes, and you just want to get a job done, and you just want to vomit out whatever you can think of and have it happen, great, have at it. Perl's awesome. I've coded a lot in Perl. I've written OO Perl, very maintainable Perl in some places. Like, I don't want to ding Perl too much, but at the same time, that instinct from someone to like overcomplicate code or take pride in wrangling complexity is toxic. It is like, run away from programmers who you ever see that in. Send them to me. I'll try to educate them. But it's like the job of code is you got to make it as simple as possible for your sake and others. We want things to be really, really readable. Readability is by far the most important thing in code. And team context is super important, a point I made earlier, but now I'm remembering again, right? It's not that there's ever like one way to write code, or that there's one set of idioms, or that there's one perfect way to do things, or as we've seen in like tab space battles, although I hate that one, just let a formatter deal with it, team context matters, right? Because whatever you establish as being idiomatic within a team is what's going to be easiest to review. Like, the point is not to do things that are obscure or uncommon for the set of folks who have to use it, right? So if an abstraction simplifies things, great, but you then have to use that abstraction quite a bit so that people stay familiar with it. All right, I said that functional programming can change stuff at runtime, and that was a bit confusing. And so I don't mean to imply that there are no statically compiled functional programs out there. There certainly are. And modern machines even really heavily discourage runtime changing of code, right? Like, it's pretty, a lot of operating systems and environments these days say, a memory page can be executable but not writable. you can't be both, right? And they've built in this security expectation for good reasons, and things like runtime optimizations and have to do backflips to cope with that kind of stuff, and it doesn't really cooperate well with some traditional functional programming techniques. But still, functional programming does kind of at its core teach you and tell you, yeah, your code in a function is just data that can be also be manipulated and changed on the fly. Macros are a good example of how that can be done. It's not like the fact that that's not a common thing that you see in real world code tells you it's just not that useful, but it is an interesting concept to break your mind and expand your horizons and learn from and remind things. And I will point out that static programmers or programmers who write code in static languages can often miss that actually runtime optimizations can be the most powerful optimizations because they can be data dependent, right? So if something can observe how often a branch is called based on the data and see, well, that branch is much more likely than this other branch, not based on our guess, but based on the actual data. So let's move that branch up a bit in the actual compiled instructions so that that's, in a better spot for the CPU pipeline and prefetcher, right? That's like an example of an optimization you can only do at runtime, right? And stuff like that, or like dynamic loop unrolling, or dynamic function compression, or inlining, those can only happen at runtime, and they're actually quite powerful in my experience, and underused. That's an underdeveloped field of computer science, all right? And in some ways, that executable, writable, mutual exclusion bit on pages is fighting against those optimizations. So there you go. Cool. All right, what else? You can do all this in Python for sure. Saw a comment there. So Python you can definitely use functions as data. Let's see. A lot of comments about my streaming and making the window bigger. I talked about the small target environments like the dash buttons. Kind of go deeper into the high watermark. I think we made that one clear with the highest position of the right cursor. Yes, we're applying type safety to I/O. And the state machine we mentioned earlier, the if statements are basically transformed into that declaration instead. Composing API calls does make things easier to debug and prove behavior. Yes, we formally verify S2N, and a lot of this work makes it easier to formally verify. In fact, we were able to formally verify our implementation of HMAC in about 5 to 6 weeks, compared to 2 years for OpenSSLs, and I attribute most of that to how we structured it. We get some pretty, without even trying detailed performance improvements. When we initially wrote S2N, it was about 3% faster than OpenSSL, and most of that came from just simpler arrangement of code that was just friendlier for the compiler. Do we check errors? How do we check errors when we compose functions this way? S2N has its own internal idiomatic error checking system where basically every function is expected to return 0 no matter what. And if they ever don't return 0, we've got these guard functions that are essentially exception handling for C. And that's its own thing that's in S2N. That doesn't come from functional programming. That comes from OO, right? And exceptions. All right. Any recommendations for practicing thinking about this in the design phase? So I honestly recommend picking a programming language that's about as unlike any you've known before, except maybe like Brainfuck or one of those crazy ones. But say pick a Lisp or Scheme, and really sit down and try to code in it, and it'll suck at first, and be really hard, but it's worth pushing through, and it is mind expanding. And you learn a lot more from that than the next similar amount of effort in a language you already know. What's my favorite go-to food place pre-pandemic? Oh my god, I don't know. I used to have breakfast at Lola and then they shut down. So annoying. Hopefully they open again soon. But at the moment, I'm Butcher's Table. I went there for lunch yesterday in Seattle. Really, really good. Am I going to talk about provable correctness of the state machine? So we did prove the correctness of our state machine. Actually, a partner company we work with, Galwa, did most of the work there. And they were able to find state transitions, valid state transitions from the RFC, the standard, that we didn't cope with. Now, those led to those didn't lead to security issues. S2N would just abort the connection in cases like that, but it was cool, and it was, I hope, easier to verify our state machine because of how we had structured it than if we built it on if statements and switch statements and so on. What is the red phone for? Oh wow, I should go back on main view so you can see that. This red phone beside me, I'm surprised no one's asked this before because this comes up a lot on Amazon video conference calls, is so building codes, at least here in Washington State, for tall buildings like this, maybe any building above a certain occupancy, say that every floor has to have an emergency phone. And that emergency phone has to be as old school as it comes. It's just a regular POTS phone that uses like the plain old telephone system with an RJ11 and gets its power from the telephone line. So then if you lose power or network or Wi-Fi or anything in the building, the emergency phone still works and somebody can still dial 911, right? So very sensible requirement. Now, this is not the emergency phone for this floor. That's on the wall where it should be. But it is an emergency phone. These are the only phones they still make, basically. The only POTS phones that are still sold new, because there's this market for it as emergency phones. So they're all red, right? Which is pretty cool. And this is a rotary one, though they do have pressy ones too, but I like the rotary. And it's a real normal POTS phone. And this one is dual wired. So it's got a phone number. You can call this phone. It can make phone calls. And it's also got a Bluetooth extension, so I can use it as a Bluetooth phone or Bluetooth microphone and speaker, which I occasionally do on video conferences. And I could try to do now, but I'm afraid would break the Twitch stream. Let me see if that. No idea how to do it here. So, it's pretty cool. And I originally got the phone because I'm part of the AWS Call Leader program. So if we ever have a large scale event here at AWS, like something's down or could go down, we have a call going, and it's my job to coordinate and lead those calls across the company. And I got that phone as part of that program. So there you go. All right. What's the difference between functional programming and declarative? I should have been clear about that. So, functional programming generally, refers to that programming languages which are more inspired by like Alonzo Church's work and the Lambda calculus than imperative languages. And it's kind of a fuzzy definition, but like you kind of know them when you see them. And they like the name suggests, use a lot of functions, and they compose a lot of functions, and they treat functions as data, right? And that's what makes a functional language functional. Declarative programming, right, is when you try to write, instead of writing instructions or do this, then this, kind of like a recipe style, you instead have these declarations that are just descriptive about what something is, right? And so I would say the state machine was a good example of declarative programming, right? Where we've got these, it's not a recipe of do this, then this. It's this declaration of like what a valid set of state transitions is, right? And functional programming often tends to go with declarative programming. Like you'll often see a functional programming language define a dialect for parsing a declarative style somehow. Just really, really common. Am I giving a talk at reInvent this year? Yes, 2. I will be there in person also. Should be fun. People are dissing on Perl. Fair enough. Someone says, well, compilers do things like inlining, branch prediction, unrolling. Yes, they do. But in general, a compiler only does them when you compile the code. And so it has no idea whether its guesses are really right or not. And so runtime optimization, which can actually see, well, what's being called, can actually do better than static compilation can often. Do I have thoughts about using databases as the source for state in state machines? Yes. Don't. That's a terrible idea. If you, I mean, sometimes you've got a distributed state machine. Maybe you're using Lambda or a serverless framework to parse different states in a state machine, and so you need a coordinated place to maintain, well, what state am I in, what state comes next, and so on. And databases are a common place to do that. I think it's really, really hard. I've seen it go wrong a lot. And I'd really encourage someone to look at step functions or something similar to step functions, if there are competitors out there, I don't know. Because they abstract away a lot of the harder problems for you. And step functions works in a similar style where, you give it a declaration of state transitions and states, and then it just calls the functions for you, and you don't have to think about how to serialize and deserialize the state itself. So that's what I think. But that's my biased opinion based on getting burned by having databases do it. All right, what else? Do we fuzz test or similar? Yes, we fuzz test a lot in S2N. We've got fuzzes running 24/7. We have to do some special things in S2N to fuzz test. It's really hard to fuzz test cryptography because the inputs are random, right? Or random looking. And so you can't really explore or directly fuzz test a cryptography library. You have to give it a secret bypass to get past the cryptography and go directly to the message parsing. And so we built a little framework that basically, pretends things aren't encrypted, or pretends things are encrypted, but then lets the fuzzer exercise the actual message parsers, which is the important part. Cool. All right, someone's recommending the Builders Library article on constant work. Have at it. I enjoyed writing it. Cool. Someone learned C by writing a Lisp. That is a great way to learn C. And yeah, Lisp will change your world. It's crazy. All right. Can I do a stream on formal verification with real software? Yeah, happy to. We've got a bunch in S2N, so we can definitely go over that. We might even maybe try to formally verify something in real time on the Twitch stream. It'll have to be simple, but can definitely try to do that. It'd be fun. Great. That is everything in the chat that I caught. Thanks everybody for joining. All these videos will get on YouTube at some point when I stop being tardy, and all that's stopping me is I have 2 videos to stitch together, and then the rest I just have to crop a bit, and we'll get that up. And if you've got other topics or suggestions, just send them to me on Twitter or here, wherever. Any way you can get them to me, and I'll keep them in mind. I've still got a pretty healthy list of topics for the next 4 or 5 maybe. Who knows what order I'll do them in, but after that, I don't know. I'm really gonna have to start getting creative. But I'm sure we'll all figure it out. All right, thanks again, everybody. Have a very good weekend. Enjoy. Oh, wait, shuffle sharding. Oh, I should put that on the list. Yeah, that's a good call out. That was not on my list, and it seems really obvious. Cool. All right, have a good weekend, everybody.